Oh, yes, yours.
No.
Sort of close to mechanical.
It's just like that.
Yeah.
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 From CS.
I don't think there's specific field of mechanical engineering.
I'm ready to change.
Okay, see whether this works at some point or not. Yeah, it's not so bad. Where's the stupid mouse pointer? Oh, I hate it. Any image, this looks like crap. Okie dokie. Well, let's see whether this works.
Two more minutes. For those small and late. By the way, this is Joseph. He's one of your TAs. The other one may come, I don't know yet. We'll find out. So fine, my recording the last time recorded at least something, but the sound was terrible. I'll try this differently this time, so we'll see whether it works. It'll be interesting.
You should double check whether my microphone level is on the right level. Yeah, this.
You cannot download the video, or I mean, we just can install it in the web.
You cannot download the PDF.
No, the video, the recorded lecture.
You can watch it.
So yeah, just watch it.
Yes, you watch it. You want to download it? I can do this maybe at some point. Then I have to store it somewhere in the second time. But right now, I just put it on there. Maybe I make download it. Okay, so today will be more dry. Last time was fun. This time is dry. Good. We need, what do we need? Textbook. Okay, you guys get access to the textbook somehow. You will find that partially I have chapters of relevance on the web as copies, most likely semi-legal. You can use that, but the textbook is important. Read in this book. Whatever I'm talking about, if you read the book on top of that, it will be much more revealing to you. The textbook is really well organized and nicely written with good notation and good development. And you will see I follow the textbook occasionally, literally to the page. What I want to do today is essentially just remind you of a little bit of linear algebra and the basics of calculus and things which we're going to need in this course. And again, the textbook has a really nice chapter. This is at the end, it's an appendix on this topic, and I'm going to use just the textbook appendix to go through and just highlight some of the things which are the most relevant for us. So this is stuff you will see again and again and again. Please do not ever come and complain to me that you have not heard that this course needs a little bit of linear algebra and a little bit of differential calculus. If you do that, just go away. As simple as that. That's not going to happen. Hey, there's the other guy. This is Harry in Peel. another thing. They need keys, you don't. You're not special enough. Only those are the keys for the conference room here. Good. There were some questions hopping around. One about the teams. Please form teams which last for the rest of the term, ideally. Obviously, you can swap people in and out. It's a little bit new to do basically a couple of labs which prepare the project. In the end, basically, what is the project about? The project is about giving you an opportunity to work with a real robot and have some fun. And all of this, what we're doing here on a theoretical basis, suddenly will hopefully make more sense when you start applying it to an actual robot. And it's really for you. It's a service. It is not that I don't know how to grade people based on projects in a particularly sensible way. That's why teams are totally fine. You're just meant to have fun. It's fun. It's a real robot. It's very cool. Not many people get access to an actual robot. In a robotics course, not many people get access to a $10,000 robot to play with. So just enjoy that and have a decent team with friends and colleagues or some good mixture of people you get along with. And then stick to this team throughout the project, throughout the course if possible. I don't care if you swap people out in the end. I just in the end need to see that everybody was part of a final project and accomplished something. Let's see. Any other questions? I work on the improvement of the recordings. We'll see. This is now a different way. So you will notice that what I'm recording right now, you will always get the screen of the slides as the biggest window. Unfortunately, I cannot change that. This could actually be slightly smaller. And now this time you will get actually two camera streams. One is essentially me. Oh, well, it's the whiteboard. If I'm in front of the whiteboard, you will actually see it. And the other one is just a second stream, which basically takes my camera and points it at that screen one more time, so you can see me pointing around in case I point around. So that should hopefully give you a full picture of what's going on. And the sound quality is now coming from my microphone instead from the room microphone, since that seems to be inferior, the room microphones, maybe because all of you are scratching yourselves so much. I have no idea. Good. Let me see, is there anything else? I put on the syllabus for the rest of the month. Next week on Tuesday, I will do a remote lecture that will be also exciting, interesting, new. And Thursday, one of my senior students, actually, he's by now actually a PhD, will tell you about Ross. He's a super duper expert in the robotics operating system. And he's going to disappear by the end of this month, so we just got to grab him before he disappears and give a lecture, since he's really good at that. He's not been hired by Google Robotics. Good. And then I'll update what's happening in February. In the end, the lectures will roughly stay the same, so don't. It's just exactly which lecture at which time will be a little bit changed. For instance, I usually was talking about hardware components much later, like in March. I may actually pull this forward, since if we start looking at the now robot, which I want to do fairly soon, I bring one here and we play around with it, and you see a little bit what's happening. I want you to understand the hardware components a little bit better. So it might be useful to just do that kind of, from my point of view, fairly dull hardware lecture before. It's just telling you about, hey, that's a sensor. It's cool. But it's actually worthwhile knowing about what sensors are and how they work and what are the goods and bads, since you will figure out that despite robotics has now progressed a fair amount, sensors, actuators, we are not in the hottest part of the world yet. There's a lot of mechatronics and research to be done to improve that. Okay, good. So let's get through that. That's as much fun as that is. So, linear algebra. Appendix of Siciliano and Schiaviccio. I want to go through all these basic things again, reminding you, vector matrices, basic notation which we're using. Inner products, linear systems, eigenvectors, eigenvalues, transposes, outer products, matrix inversion, vector calculus. There's more in the appendix, but these are the kind of most important things you will see throughout the course. It's not complicated. You should have seen that before. I'm not sure how long ago. We'll find out. And it's just reminding you, if you've seen this before, just, yeah, that's it. It's not so exciting. Now, how do I scroll now? Let me see whether I can do this. Any scrolling going on? No. Where's my mouse pointer? Here. Good. Ooh, yeah.
Okay, this is in a full screen mode as it appears. Is that? Well, is this readable? Readable from you? Yeah? No? Oh, come on. What's wrong with your eyes? You're young. You're supposed to do this all beautifully on the fly. Okay, so how do I do this smaller? What's my menu bar doing? Window. This zoom. How about I zoom the window? That was interesting. And now I zoom even more. Minimize, maximize, split count. Just, am I as incompetent as I look like? There should be somewhere. There used to be something where I can click on. Okay, fine. I'm confused. Let me get this window. Oh, they mean the place. Doesn't it advance just? Okay, fine. I'm in a very stupid. Okay, fine. You are right. Good. You passed the course. Excellent. So now it's bigger. Fine. We start with basic things. So just there's one important thing. We will follow a standard notation which many people in robotics and machine learning actually use. Not that everybody uses that, but we will use essentially capital letters which are bold-faced. And this is one of the things I will never try to reproduce on the whiteboard. Okay, the bold-faced business is too much work for me. I'm not going to draw big letters all the time. And this is usually a matrix. Okay, a little bold-faced guy is a vector. And usually an italic guy, and that is again totally beyond my abilities. Let's make it a little s. It's a scalar. Okay? Now, so this is very easy. A matrix, reminding you, is shown here, is something which has columns and rows. Okay? These are called the rows, and these are the columns. Awfully exciting. Vector, now vector is kind of an interesting little guy. What is it actually? It's a degenerated matrix, if you want. Okay. It could now be something which looks like this, or it could be something which looks like this. So it could be what's called a column vector or a row vector. Now, by definition, that's our personal, private, super cool definition. We will simply say a vector, if it doesn't have a transpose sign, we'll talk about transpose in a second to remind you, is a column vector. Okay? This is just a personal, private preference. Many people use that, not everybody uses that. A scalar, I cannot tell you anything about a scalar. It's just one little guy. It has no interesting dimensions, neither to the right, nor to the bottom, nor to the up. Okay? So this is what we use throughout. This is what the book uses throughout. And I hope I use that on all the slides consistently, typos excluded. Good. Now, what do we have here? So matrix coefficients are notated by aij, for instance. So you do just some, you want one little guy out of the big matrix, you can make this aij, for instance, and get out of there. Sometimes people denote entire columns of a matrix by making a notation like this. That's a column. This is a little bit more idiosyncratic. Let's see if I scroll. Yes, this works. What do we have else? There is generic matrices, and they can have certain number of rows and certain number of columns. Boring. There are more interesting ones, which are having the same number of rows and columns. They are square matrices. And then they can have structure. And that is actually something which we exploit frequently. So a matrix, for instance, can be, what do we have here? Interesting things. First one can be upper triangular. So this is shown here. That means you have only non-zero entries on the diagonal and the upper triangle. And then obviously there's a lower triangle, which is just having the opposite in the lower.
This is just silly notation. Why do people care about this? It's just sometimes the math will be simplified, if you know these things. Very important, a diagonal matrix has only non-zero entries on the diagonal. It's a very friendly and easy to work with matrix. All these kind of properties matter partially also when you implement things on a computer. If you know that there's zero somewhere, don't multiply zeros with each other. It's not very brilliant. Just wastes time. Let's keep going. Hey, look, here's this actually as a footnote. I never noticed that. How do I get to the next page? It's the question of the day. Okay, see whether something happens if I get my mouse pointed down. Okay, next page. What was the abbreviation for next page? Show next, oh, arrow, right instead of down. I'm an idiot. Transposes. A transpose of a matrix simply exchanges columns and rows. Very simple. So V for vector, V transpose now becomes a row vector. It's very simple. The same coefficients which you had, like A1, A2, A3, blah, 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 now becomes A1. You'll have this many times, and it's a useful thing to do. Same, the matrix, you just take the columns, put them in the rows, and the rows in the columns. Nothing profound. What else do we have here? Symmetric matrices are matrices where the upper triangular matrix and the lower triangular matrix, now we can talk about this, are mirror images of each other. Or you get the A11 and A11 happens in, if you just mirror it along the diagonal, they are the same. Now those are really important, and those we will need a lot, since many physical systems have symmetric matrices because they are about physics. So this is the interesting thing. Linear algebra is linear algebra. Now we are also talking about physical systems, which have things like masses and inertia. They're described by linear algebra, but have special properties which come from the physics of the system. And that allows us actually to simplify a huge amount of math and have certain properties which are really useful. Then, what else do we have? We have skew-symmetric matrices. What the hell is that? So, what is that? If a square matrix, this is now alpha square matrices. It's said to be, so also, a symmetric matrix has to be a square matrix, otherwise the symmetry stuff doesn't really work well. A skew-symmetric matrix is A transpose equals minus A. So, that means the upper triangular thing is the negative of the lower triangular thing. Again, we will need this in some kind of coordinate transition. But why do we care so much about matrices? We will soon, not initially, but starting with February, we'll have to describe robots which live in a 3 or actually in a 6-dimensional space if you want to. They have 3 positions, but they also have 3 orientations. And we need to move through these spaces and transform along robotic links to get, for instance, to the hand space. And we will have to describe coordinate systems, and coordinate systems are nicely described by 3-dimensional matrices, for instance. Actually, 4-dimensional matrices, as we will figure out at some point, or if you really wanted to, 6-dimensional matrices. But we won't go to the 6-dimensional stuff. We'll just stay with 4-dimensional ones. Another nice thing, matrices or matrix algebra in general can be written in partitioning. So if you, for instance, have submatrices in there, well, fine, it's just a bigger matrix. And you can do the entire matrix algebra also with submatrices as the coefficients. This is just often more convenient to describe rather than writing all the coefficients out. So for instance, if you want, what you will see at some point, there's something which is called the homogeneous transformation matrix. And this one will be described by having a rotation matrix in here, a 0 vector down there, a translation vector over here, and a 1 there. So that's a partitioned way of writing it, which is much more telling you something. Rather, writing it, if I would be writing 4x4 coefficients there, which are just coefficients. Cool. So fine, you can also basically write transpose vectors in the rows of a matrix, whatever you wish. So you can now play around. Just make your life easy. Any help needed back there? No? Happy? Good. Happy is important. let's see. Now going down was this thing. Hey, this works. Good. Let's see, what do we have here? Matrix algebra. Not particularly complicated. Boring. A plus B is C. This only works if the two matrices have the same shape, same number of columns and rows, and you just add the coefficients up. So that is super simple. Nothing interesting. Then you have simple algebra rules, which is the same rules as for algebraic equations or scalar equations. Nothing exciting, so you can commute things and do things like this. The fun thing is that a square matrix can always be written in terms of a symmetric matrix and a skew-symmetric part. This is sometimes useful for decomposition. So here's A is a square matrix. Up here again. I have no idea how visible this is actually in the video. To be expected later. So A in general, if it's a square matrix, can be a symmetric plus a skew-symmetric. And you can actually compute those components, which is actually useful. So this is 1/2 A plus A transpose, and this part is, I believe, 1/2 A minus A transpose. That's correct. And that allows you to basically extract certain parts of what the matrix is doing. We'll talk in a second about what matrices are doing in general. Multiplication of matrices. You guys hopefully remember how this works. Not, check it out. A times B equals what? And you basically have to now multiply the rows of the first one with the columns of the other one, and do this for every coefficient and every combination, and you get the combined matrix. Very important, okay? B times A not equals A times B. That is something people love to screw up when they forgot about this. This is really, really bad. Don't do that. You can always think about it. It's very simple, you know. I can multiply, for instance, if the matrices are not square matrices, I can just draw this like this. So here's a vector, or here's a matrix, say, with 2 rows and many columns, and here we just have 2 columns and many rows. Now they have to be compatible to be multiplied, so the number of elements have to match. If this were suddenly that I try to multiply this with this, you would get a totally different result. The matrix size would be totally different. So it cannot be the same ever. So it's actually very intuitive. Good. Let's see what comes next. Next page. Here come multiplication rules. Yeah, so little important things. Transpose operator. You need that. Equals, what is it? B transpose times A. So things reverse in sequence. That's important. It happens also in inverses, as you'll see in a second. So now comes for moment determinants. We don't really need determinants a lot, but they are a useful component to check matrices. So what are matrices for us? Most of the time in robotics, a matrix spans a space. Now here, like, I can give you a very simple matrix, which is a nice matrix. If I just want a Euclidean space, X, Y, and Z, and I want to describe that, well, that's not a particularly tough thing to do. I just take a matrix and have a 1, 0, 0 vector, 0, 1, 0 vector, and 0, 0, 1 vector, which simply says that my first axis, the x-axis, points in this direction. This is a unit vector of length 1. It has no components in y and z. And the same happens with the y-axis, happens with the z-axis. So this is a space. It's a nice space. It's a happy space. It's a full space. Now, the determinant of this thing should be, let's call this
A sense and write determinant of A1. And that means that it's a happy matrix. There's nothing wrong with it. Interesting is, if this were a 0 here, then the determinant becomes actually 0. And that tells me that this matrix is cheating. It tells me that it pretends to span a three-dimensional space, but in practice it does something degenerate. So determinants in some simple way, the way we need it here in the course, can be thought of as a way to check about the degeneracy of your space. And it's not always going to be perfectly zero. We work with numerical systems, so the coefficients are not going to be beautiful ones and ones and ones. They come from other things. But if something goes wrong with your linear algebra, like you get NINs or something, just running things and checking determinants of some matrices can help. And one of them is 0 or very close to 0, like approximately numerically 0, you might notice that something is going wrong. So in some sense, it's a little check tool for us to understand what the matrix is doing. We go back to this in a second. We actually look at what is called singular value decomposition, which is a much more powerful tool to describe this. Determinant is just a little check on this. Okay, that is really all we need about determinants at this moment. There's all kinds of little algebra about determinants, not too complicated. What do we have here? Rank. Okay. The rank of a matrix is essentially similarly related to the determinant. It tells us how many dimensions the space is really being spanned. Now, 3x3 matrix, as I showed originally, has rank 3 since it spans a three-dimensional space. If I make this a 0, it has actually rank 2 since it only spans a two-dimensional space. And all of this is super clear in this simple matrix, but it becomes interesting if you have something like a 10 by 10 or 20 by 20 matrix with lots of weird stuff in it, which you don't really understand as nicely anymore because it doesn't relate easily to a coordinate system, which we have. And then the rank can help you to analyze what's going on. Like, for instance, if I give you a rectangular matrix, like, I don't know, A1, A2, A3, A4, and then actually A11, A12, A13, this is just annoying. A21, A22, A23, and A24. Now, what's the rank of this matrix? Who votes for 8? Nobody? Good. Otherwise you would be fired.
Depends on the value.
No, the rank can only be 2. That only the rank, this thing can never span more than a two-dimensional space, even if it has 4 coefficients. It may live in a 4-dimensional space. That's totally fine. But with 2 vectors in a 4-dimensional space, you can only span a plane. That's all it is in life. Yeah, that's what the rank tells you. Then, I'm colliding with the computer, which now shook everything. Fine. Do we already do inverses here? Fine. Yes. Inverse matrices. So, inverses are important. Very important. And annoying. So, the inverse of a matrix is simply defined if you take I minus 1 multiplied by A, it's going to be the identity matrix. The identity matrix is a happy matrix with just 1 on the diagonal and zeros out. Okay? That's a definition of an inverse. Now, in some sense, what does it mean? Matrices have many interpretations, but in some sense, a matrix you can interpret it as if I'm a happy little vector, we will talk about this, I'm a little vector V, and I get multiplied by big A, I'm going to be a happy little vector, call me W. And I get transformed in a new space, which is totally cool. So initially I was here, and suddenly maybe I don't know, in the comments. I got translated, and maybe I got rotated since I'm lying on the bed now. Pretty cool. So this is what this thing is doing.
And what you sometimes want is you want to transform yourself back, since you want to be back actually in this lecture hall. And for that, you need the inverse operator. So you need basically W times and the inverse matrix should hopefully get you back to B. That's really what we're after. Now you can think about all the misery in life. Now, if this matrix, for instance, is rank deficient, you will become shorter. Actually, you may be mapped to 0. We'll talk about this. You may disappear entirely. And then, if you have disappeared, think about it. How can I regenerate you after you've disappeared with an inverse matrix? It's not going to work. And that is basically what we'll learn, or we will see sooner or later, that the inverse is not always existent. Depending on the properties of the matrix, I may not be able to take an inverse. So for instance, if the determinant is 0, the inverse will actually blow up. It will not be existing. And a lot of what we're going to do in robotics is we need to go through coordinate systems. We transform back and forth. We have to invert something. You want to create a motor command which creates a particular movement which I want to do. It always quickly involves inverses. Inverses are a major pain. To be honest, linear algebra should be abolished entirely. It creates a lot of trouble. The concept of inverse matrices is annoying. And from a machine learning point of view, we're not going to talk so much about it. Sometimes maybe the wrong thing. Since you suddenly create infinite numbers just because your math is weird. The reality is, you know, if I got transformed somewhere and something is rank deficient, I can never be nothing, and I can never blow up to infinity. None of this is actually possible in a physical world. When it comes to linear algebra and physics, there's sometimes a mismatch, and we'll talk more about this when we talk about inverse kinematics, inverse controllers, and you will see a little bit more about this. But there's something weird about this. So you should always doubt everything in life, okay? Including linear algebra, despite its truth. What do we have? The inverse of an inverse, no, I don't have to write this. Inverse of an inverse is just the matrix itself again. The inverse of a transpose matrix is the inverse matrix transpose, so simple rules. And in very special cases, there's something with if a matrix is orthogonal, the transpose is the inverse. So this essentially means that all the rows of a vector of a matrix are perpendicular to each other. So the vectors span a perpendicular space of unit length. What's the normal? Well, you can always think about this, what this means. If you have a matrix A which looks like this, you multiply it with its transpose. This is a transpose here. And now all what we did, we put the rows and the columns and we multiply them together. These are becoming inner products. We'll talk about this in a moment, but all the inner products have to be 1. And only then it works. We'll get back to this. You will see more of this. Trust me, a lot. Too much. Important, the AB multiplication of two matrices inverted is, again, changing the sequence. It becomes B minus 1 times A minus 1. Again, these are the simple rules. There's lots of little rules. There's actually, you can get, if you look around cool rules of linear algebra, you get something like 10, 20 pages of the most common rules. And basically, your ability to manipulate equations basically depends on how many of those rules you know in life. Good. What do we have here? Here is a thing which actually is one of the most used theorems throughout, I think, robotics and also machine learning. This is called the matrix inversion theorem. So why is this pretty? Basically says if you have the following form, you have a matrix A plus B, C, D multiplied with other inverted, you can write this in form of this thing. Nobody appreciates that beauty. What is nice about it is that essentially I write the entire expression just in terms of an inversion of A. And a little C inversion, but often this goes away. So let me show you an example where this kind of matters. And this is just an example where you have, now let me go into this notation up there. You have A, and you want to, let me see, here's the sequence of this. You have A, and you need to invert it. And now you want to change A. For instance, A could be now changed by a data point, the vector, which is now multiplied with its transpose. This is what's called an outer product. We come back to this in a second. So now you want to inverse that. Okay. Now, an inverse operator on a digital computer takes n to the 3, so n cube operations roughly. N is the number of elements. This has to be right now a square matrix. We come back to non-square matrices in a moment. Okay, so you do this inversion, you basically spend n cube operations, and now you do this again. And that is annoying. Now the beauty is, if you use this theorem, you can actually write this here in a different way. And this is going to be A minus 1 x transpose A minus 1 transpose, I believe, and 1 plus x transpose A minus 1 x. And that is just an order n square operator, because it's just matrix multiplication. You can reuse the inversion which you've computed one time and just add the other stuff to it. So this actually special version of the matrix inversion theorem is called the Sherman-Morris-Woodbury theorem, which is an even worse one. But this is why this is actually important. And there's also essentially a matrix version. If you have a matrix which is partitioned in a particular way, in A, D, C, B, as shown here, and you need to invert that. And again, these are submatrices. Then you can basically write the inversion in form of that, and you have some definitions of some additional symbols. The whole idea is that becomes numerically faster to compute. And you can do analytical algebra things to simplify equations. Often you can actually use that to make things way more efficient to compute. So people like this thing. Now let's go to the dot stuff. You all remember dots? Differentiation. So we have a variable which is a variable of time. We most of the time omit this kind of writing that this is actually time dependent, unless it's super important to write that. In robotics, almost anything is time dependent. Okay? So we just write this here. And if I want to know how it changes over time, well, I take d dt of x, which can be approximated as x at the next time step if I do it digitally with little time steps. So I can make this here t plus 1 minus xt divided by delta t, which is t plus 1 minus t. This is the time step I've been using. Okay? And then you make this delta t tiny, 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 and it becomes x dot, which in position variable would be the velocity. We have dots on other variables, so we can have the change of force, for instance. It's just, we cannot show as a position. Okay, you all remember this, hopefully. If you apply this to matrices, it's very simple. All differential calculus for matrices can be derived by just applying it coefficient-wise, essentially. Just have to make sure that you do it right. So the derivative of the matrix is simply the derivative of every coefficient of the matrix. So this here says it goes over all rows and all columns. Good. Then there's cool little theorems, and that you could derive yourself, for instance, by just doing all of this. You basically take the inverse and want to take the time derivatives of that. And that will take you a little bit of work, most likely application of this theorem, to actually show that this is the inverse times a dot times the inverse. So that is not so obvious. And then what else do we have here? The gradient of a function. What's the gradient of a function? Now we're basically going away from time derivatives. We have two kinds of derivatives. We have derivatives with respect to time and derivatives with respect to other variables, okay? The one are absolute derivatives. Remember the d when it looks like this, and then there's the delta d, which is a partial derivative, where you only care about the variable of interest. But if I take a time derivative of a big expression with lots of variables, I have to think about every variable. If it's possibly time dependent, I have to take the time derivative of it. So, like if I have ddt of, let's say, x plus c times c plus square root of, I don't know, some other variable stuff. Now I have to go take the derivatives. Is x time dependent? Is d time dependent? Is c time dependent? Is d time dependent? And do all the derivatives, chain rules appropriately. Chain rule, you guys know chain rule. Favorite, right? If it were dx of the same expression, that's easy. Just one. There's only one x which appears. That's partial derivatives. Now the gradient of a function of x is again, it's a vector, is the partial derivative of every coefficient of the vector with respect to x. No, it was not well said. It's the partial derivative of the function with respect to every coefficient of x. Now, that worked better, and it becomes a vector. Okay? So it's df, f, okay, very important. We have two kinds of functions. We have scalar functions. And if I could do this nicely, I would make it fast. And we have vector valued functions. I can actually make my life a little bit easier if I want to make this explicit. I can just write f of x. And I can make a little arrow on top of the f of x, so it makes my writing simpler. Okay? This means that this function produces a vector. This here means this function just produces a scalar, but it depends on a vector. So x here is always a vector. So the derivative of a function which depends on a vector needs to be taken with respect to every coefficient of the vector. Like this, and it becomes a vector. And by definition, we simply say this derivative has to be a column vector. That's why we take the transpose. He writes it as a row vector, it takes the transpose, it becomes a column vector. Okay? And it's called the gradient. What's the gradient? Just reminding you, many things in linear algebra have some kind of intuitive component. And the gradient is best done in the mountains. Okay, here is a beautiful landscape, which I try to do with geodesics. I don't know, looks like a cake to me, but fine. I just try to get there mountain. So two mountains, actually. And you're standing here. And you want to know the direction of steepest ascent or descent. And that's what the gradient gives you. If you can describe this mountainous landscape in 3D as f of x, we are basically f of x. X is now a two-dimensional vector, which lives on my plane. It's Mother Earth, if you want to. So x1, x2, and then f of x would be this, which is the height of the mountains. Now this will tell you the gradient now, dx, will tell you the vector of steepest ascent. So how do you get up? It's not the direction to the summit, okay? It is where you are, what would cost you the most effort to go uphill. I can give you a city landscape where basically this here is the steepest direction to go uphill, but the shortest path to go to the summit would be this way. The gradient is not always the shortest path to the goal. It's a very interesting little thing, which is used in many algorithms to improve gradient ascent or gradient descent methods. Okay? We need those gradients all the time. They're important for us. Okie dokie. Yeah, this. And then we can also think about the time derivative of a gradient. So this is shown here. F dot is ddt of the gradient. And then you just basically have to apply the chain rule. Oh no, we want to, sorry. We do the time derivative of a function like this. ddt of f of x is first the
derivative of f of x with respect to x times time derivative of x. You could also be written as x star. And this is where the gradient comes in. And the velocity. So we need those things a lot when it comes to describing how things move in a different space. So the function f often in a robot, so let's take a nice little robot here, has an arm and a hand. And it wants to have, let's say, an apple. So in order to describe basically how this apple moves through time, I need to know where the apple is. Well, the apple is described as some function of all of the variables of the robot to the joint angles later on. And then it changes over time. And then I basically get this kind of a gradient times the velocity of the apple, and this is how I can track it in very simple words right now. We'll go into real detail for that. But we need those things. They're very simple and they're useful. One step further now, we just make the function f a vector valued function. It's now called g to make a difference. Now g is fat, boldface. And now what you get is a vector value function differentiated with respect to a vector. You have to basically now differentiate every coefficient of the vector valued function. This is really hard to say. With respect to every coefficient of the vector x. Now let's assume we have n components in this vector here and n components in this vector x. Then as n by n has to be an n by n matrix, and that's really what comes out of it. So you basically get for every row, the first coefficient. This is basically now applying this what we did before, just row-wise. So we get the first coefficient g1 of the function with respect to x as a row vector now. That's again just a convention. Second coefficient with respect to x, a row vector. And this entire thing is called a Jacobian afterwards. People in robotics talk about Jacobians all the time. I love that thing. Good. But it's just a generalization of what we did before with the scalar function. Now, time derivative of this is exactly the same game. You take the time derivative of g, so you take basically first the partial derivative with respect to x, and then the time derivative with respect to x. And that becomes a Jacobian times x dot. Happy? Good. Oof, so much fun. I told you it's going to be dry. What do we have here? Vector operations. Do you care about vector operations? Fine, there are some things which are useful. Given n vectors xi of dimensions m times m, they are said to be linearly independent if the expression k1 times x1 plus k2 times x2 plus blah 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 equals hold for any k except zeros. All what this says is basically, if you want to span a space, all the vectors have to point in different directions. That's really all it is. Fine. You can basically then take these x major vectors in a matrix and just say they're spanning a coordinate system. Let's go into more direct things which is useful. Fine. Vector algebra, very similar as algebra for matrices. Addition is clear. Boring, boring, boring. Multiplication of a vector with scalars is trivial, nothing interesting here. This is not so important. This is what is more important. The inner product, because that's what we're going to need all the time. Inner product of two vectors, x transpose y, is a scalar, okay? You're having a vector which looks like a box like this, another vector which looks like a box like this. You just multiply the coefficients together and add them up. So that has to be the sum of xi plus yi. Oops.
So this is just a rule. But the inner product is important. It means something geometrically which is really useful. So here is one vector x, and here is one vector y. If you take an inner product, it essentially means you're projecting one vector on the other one. So you can think about this. You're projecting x on y. What component of x is in the direction of y? Now this is not quite correct, so we need to be more precise. This would work really well if y is actually of length 1. Okay? Then it would really tell us if you project x on y, what component of x is pointing in the direction of y. This is the reason why the inner product can also be written. We have this here. It is the length of x. We'll talk about the length of y times cosine of the angle between the two of the angles. You've seen that as well at some point of your life. Now you understand what I said. If y is length 1, then I just have x times cosine alpha, and this tells you this direction. If y is not 1, then I could always take x times, I can just take the inner product and divide it by the length of y, and then I have the component which is basically pointing in the direction of y, of x. These kind of projections matters. We sometimes need to know if something points in this direction, what component of it can actually help me to do a movement in a particular direction. And precisely what it really boils down to is, again, take a little robot. Here's a robot. And again, a very nice arm. And now I want to make a movement in this direction with my hand. Now I have to figure out which of my degrees of freedom, my joint angles of my motors, can actually contribute to this motion. For that, I need inner product operators. I basically take this vector and, after some algebra, project them onto the direction each motor can move the arm. And that will tell me what this motor can contribute. Some motors may not be able to contribute anything. Good. Now, given this, if x transpose times y equals 0, what does it mean? They're orthogonal, the two vectors. Good. If you take x transpose times x, so it means you inner product it with itself, well, that basically just gives you the squared norm, and then you take the derivative, and you have the length of the vector. That's essentially how this guy is. Fine. Nothing exciting. And then you have some inequalities, which are obvious from all of this. We don't need those so much. Good. Next thing is called the vector product or outer product, which is not so frequently used. Inner product is seen a lot. Outer product you need to be reminded of most likely. I'm doing time-wise, okay. So here's a vector x, and I now do an outer product with y. Now this is called outer product. It's called cross product. It's called, what else is it called? Vector product, he calls it. Fine. Maybe there's a few more names. Okay. This is computed most of the time only in 3D or 2D spaces, but mostly 3D spaces. And so how does it look like? So this is how I learned it. I'm sure whether you like it. Oops. Wrong notation. 2, 3, cross y1, y2, y3. And I was told just do it, write this down here again. y1, y3, y2. And now you multiply
this with this, x1 times y2, and add, or no, subtract, minus x2 times y1. Okay, that's number one. Now we do the same thing again. x2 times y3 minus x3 times y2. And I did this actually the wrong way. I think I was supposed to start with the lower one. So we'll see how this mistakes. Fine. Brilliant. x3 times y1 minus x1 times y3. And I screwed up. I was supposed to start at the middle element, so we'll see what comes out of it. It should start with x2 times y2 and y3. Okay. So this here needs to go down here. Sorry. y1. And erase that. Use a whiteboard. So you should start with this multiplication first, then this, and then finally this, and one, then this. That's the last one. Okay. You can just put it into a computer. The interesting thing is, what does an outer product really mean? Again, we have a vector x, we have a vector y. Now they live in some two-dimensional space. And the outer product is now going to be different from what the inner product is doing. The outer product can be basically visualized as something which looks at the surface spanned in this kind of parallelogram of these two vectors, and it creates a vector which has the length of that surface pointing orthogonal to the surface. Complicated. Now, why is this useful? Well, let's think for a moment what this means. So how do you get an outer product to be 0? Parallel. Okay, just the opposite of the inner product. The inner product was orthogonal. Now we do parallel. There's no surface there. So that is useful. Where do we need outer products? So here is where this intuitively comes into play a lot. And this is a physics thing. So I have to make a nice little drawing. This is the UAC swimming pool. Okay? And here is a guy standing. And we are interested in whether this board, this springboard, can actually support the big guy. And so the big guy will have a gravity force pointing downwards, and be F. Oops, F. And this here has length L. And we are interested in what kind of a torque is generated here at the point of connection. And is that torque such that actually it will rip out the concrete foundation and the thing will just fall apart? Now, these kind of computations, F is now a 3D vector pointing down here, L is a vector pointing in this direction, are described by cross products. It will actually give you the torque. We'll come back to that. So it has a very useful application for physics. Basically, this is very intuitive, since it's essentially just 2D. We don't have to think a lot about it. You could do this in a different way. The moment you go in a multidimensional robot system, all these vectors are not so easy to visualize anymore. We just have to compute them the right way, and you know that the cross product is going to do what we want at this point. Now, cross product rules. Okay, here cross product with itself is 0 because the two guys are parallel, easy. If you change the sequence, you have to put a negative sign in there. That's very useful. Simple algebra rules. This here is a useful, very useful component. It's very unique for the first type of skew-symmetric matrix. The cross product is awfully annoying. Okay, who wants to deal with that cross notation? And the nice thing then is basically if you write x cross y, you can write this as a function s of x, a matrix actually, times y. And this matrix looks like this. So now I take the coefficients of x, x1, x2, x3, and I sort them in the matrix as shown here. And then I get the same result as the cross product. And that makes algebra much easier. Now you're starting to multiply zeros, which is inefficient, but it's, it's much easier to work with matrices than some special operators like cross products. And you will see all the time, whenever we start with cross products in some derivations, because it's physically intuitive, and then we switch to the matrix notation since it's algebraically useful. But the cross product has more physical meaning, which is useful. Okay, so here you can do then the rules of this become, if you do the cross product of x times y, it's s of x times y, or it's minus s of y times x. So you could derive these things yourself by now. And then there's some more rules which we don't need so much. Good. What else do we have? Linear transformations. So now we basically got the basic notations ready to go. And we just apply them to the first kind of systems which are useful. And one of the most common systems, actually in linear algebra, robotics, but also machine learning, are linear equations of this. So you take a vector, you multiply it with a matrix, and it gives you another vector. And it can, we talk about the different meanings of that at some point. Intuitive meaning is always you take a vector x, and you basically transform it. That means you change it into a new coordinate system, which is y, and express it in y. You can also think about it if you want some abstract thing. You take x, you pass it basically through a particular space, and see how this looks in a different space. We'll see more about this. Now, there's a few interesting things. Now, A can be a square matrix, can be a rectangular matrix. We don't care. Just the coefficients, basically the number of columns and of the vectors, have to work out appropriately. So if A is rectangular, looks like this, and then basically x has to be looking like this, and then y has to look usually like this. But I just show you the shapes to remind you that if I take the long vector x, run it through A, you get a short vector y. Now you can also remind yourself that if I get something that's just shorter and I want to inverse transform it back to x, how do you do that? It's easy to make something shorter. It's hard to make something longer and know in which direction I should make it longer, since I have a whole bunch of directions to play with. What is important is now the concept of what is called a range space and a null space. We'll have that a fair amount. And it's actually very intuitive. If I take all vectors in the world, which I run through A, and what comes out is a vector, non-zero, they are part of the range space. And all the vectors, if you run through A and out comes to 0, well, they live in the null space. It means there is a part. So X lives in a space again. And thinking in terms of spaces is the most useful part for us, at least in this course. X lives in a space, maybe a 3-dimensional space, maybe a 10-dimensional space. We'll see different spaces at some point. And the space can be partitioned into 2 parts. There's one, let's say, half or a fraction of it. If I run it through A, then there will be a non-zero result. And then there's this other fraction which actually creates a 0 result. You will be swallowed, you will be gone, and you will never come back. I cannot make you come back. This will be actually very useful. Again, where is it useful? Intuition. Here comes my robot again. I'd like to draw it many times. This is the hand. Even worse. Now, when this robot moves in this direction, I need a certain number. It's a 3-dimensional movement. I need a certain number of degrees of freedom to move. But I may have like 20 or 30. Actually, for a 3-dimensional movement, I just need 3 degrees of freedom. So what the robot can do in the meantime, it could actually move with its hand and lift its leg up. This will not interfere with my hand movement at all. Now, the way we're going to formulate this at some point is that the motion of the leg has to be in the null space of the transformation of which basically creates that motion y here at the hand. And I can show you that tape. You want to see a real cool null space. Okay. That's my task. I point at this thing. Now I'm moving my null space. Okay, fine, didn't work. But now you saw a real null space movement. So it's not that abstract after all. So for relative to the task, which was to keep my fingertip there, all what I did with my body was a null space movement. Which you basically gives you a feeling that at some point robotics is going to be a pain. Since you have often too many degrees of freedom to do something, and you will actually figure out sometimes you have too few degrees of freedom to do something. Our human arm is actually kind of cool. It's 7-dimensional. So we have 3 shoulder degrees of freedom, 1 elbow, and 3 wrists. Don't forget about the fingers, they're too many. Is this a good number or a bad number? So people have tried this, and they've done actually just some experimental robotics. Now, I need 3 degrees of freedom in order to point at every point in space, at least at some range, which is close enough. So for that, I need 3. Now, let me give me an object, and I want to orient that in a particular way. Now, I need another 3 degrees of freedom. So it's an orientation of an object also needs 3 degrees of freedom. So I already need 6. So now I have 1 extra one in my arm. This extra one is actually really useful for additional things. Like, I may want to orient something, but for instance, I may want to push now against something. Now, there's 2 ways of pushing. I could push like this, or I could push like this. When you have a screwdriver in your hand, you try to put your arm straight behind the screwdriver so you don't slip off. Pushing like this, just off you go. So this additional degree of freedom is really useful. And you will see, degrees of freedom are pain. You can use them, you cannot use them. Sometimes when you align them, like because my upper arm rotation and my lower arm rotation are now aligned, that means 1 degree of freedom is gone. I look like 7 degrees of freedom, but I'm actually only 6 degrees of freedom anymore. You will see these things. They matter for us, and that's why we need this concept of range spaces and null spaces. Okay. No, we don't need this so much. Fine. Eigenvalues and eigenvectors. Given that we have this transformation now, we can start to describe a little bit more what it's doing. You all learned about eigenvectors and eigenvalues at some point. And the definition of an eigenvector is that you have a matrix A, you multiply it with some vector u, out comes lambda times u. So this is a vector. Okay? Lambda is a scalar. So what does it tell me? It says there are some vectors u in the big space where all the u's live. If I multiply them with A, all what they do is they get stretched or shrunk, or if you wanted to invert it, then lambda could also be negative. And I'm not going into convoluted complex. Intuition is much nicer than this. So A, there's some special vectors. In this special direction, I can only become longer, shorter, or I can get inverted, but I stay in the same direction of motion. And these are called the eigenvectors. They're kind of helpful for us to characterize a matrix. Why? But if I have a big matrix, and it may actually be rank deficient, so it doesn't have enough degrees of freedom. If it doesn't have enough, it doesn't span the space which it pretends to span. If I look at the eigenvectors will actually tell me all the direction in which I can actually do motion and not get swallowed up. There will be some eigenvectors which basically point at the direction where I get swallowed up to 0. And these are going to be eigenvalues. The lambdas are the eigenvalues which are 0. If an eigenvalue is 0, that means there is a direction where I just disappear. So actually a matrix which is rank efficient may not be so bad after all, as long as I don't mess with the part where it eats me up. I can always still exploit a matrix in some direction where it is behaving nicely. If it's some direction where it gets swallowed, I may want to avoid it. Or I may actually want to exploit that, depending on what you really want to do. So this is what eigenvectors tell us. And we will need them frequently in singular value decomposition. We'll see this in a second. It's just a nicer way of thinking about that. Eigenvectors, you can get them through the
determinant of this equation and then get characteristic equations. You learned this at some point. We don't need this. Most of these things are done nicely in computer programs like MATLAB, Python, or whatever C libraries. We need for a tiny moment, yeah, we're slowly running out of time, bilinear forms. And let me go to this. Here's a generic bilinear form, which looks like X transpose A Y. Very important, this is going to be scalar. A vector transpose of A times Y is a vector, then I do inner product of X transpose with the resulting vector, it becomes a scalar. Okay? And why is this important? There's some particular versions which we care about. And what we care about in particular is what is called positive definiteness. This applies actually to this equation when we just use X instead of Y. And we're interested in the particular case where this product is always greater than 0, equals to 0, or less than 0. And this is basically, if it's greater than 0, it's called that the matrix A is positive definite. If it's equal to 0, well, then it's nothing, but it's becoming semi-definite. If it's less than 0, it becomes negative definite. Why does this matter? Here is what I'm after. A variable x, cool, a scalar, squared, is greater than 0, less than 0, equal to 0. What do you think? Okay, it's definitely greater equal to 0, depending on what x is. If x not equal to 0, then it's going to be greater than 0 all the time. So this is cool. Now, can we take this very trivial concept of squaring something and put it into the world of matrices and vectors? That's exactly what this positive definiteness is trying to do. Now I have this kind of equation, which is essentially a generalized square. It's like I put a little w, a scalar w in front of it, which I say the scalar w is non-zero. Okay, and it's if I make it greater than 0, then my equation up here still holds. That's what A is doing as well. We're interested in matrices where you apply this thing which stay 100% positive. Why do we care about this? We will see a couple of lectures down the road. Sometimes we need to prove things. We need to prove things that we get something which is called stability. That means we want that a robot always works and never screws up. The same as when you're up in an airplane, there's an autopilot. Autopilot, please work all the time. We want to prove that autopilot works. And some of the proofs require that some matrix multiplications do not change the sign of certain terms. Now, if you can show something like this, and you know that the matrix is positive definite, then you know that you will never change the sign of this term. This term will always stay positive, for instance. Or it will always be negative if something negative is in front of it. So these definitions will matter. You will see later on why they matter, but they're important. Oops. Okay. Here we have this positive definite, positive semi-definite is just when the possibility of being 0 also comes into play. What else do we have here? Is that important? These are just derivatives of bilinear forms. So if you have back this thing y, and you do d dx, or you want to do d dA, or partial derivative with respect to y, it just tells you what comes out of those equations. I'm not going to go through this. This is just rules. You could derive them yourself. I do need the pseudo-inverse quickly, and then we're almost done. So we'll get more to pseudo-inverses, but the idea now is, what do you do if a matrix is rectangular and you want to invert it? So this thing is the -1. How can you handle that? And it essentially requires some special rules. And now it means that the matrix looks like this, or the matrix looks like this. And then you have two different kind of inverses. The one is called the left inverse with a little L, and then the other one is called the right inverse. So the idea is, if you have a matrix A, and you can from the left side multiply it with AL, that is the inverse, you get the identity matrix. Or the other way around, you multiply it with the right thing, and you get the identity matrix. And so let's look at the left inverse. The left inverse looks like A left, checking A transpose A minus 1 times A transpose. And this is an algebraic construct, very simple. Let's plug it in. So AL times A is supposed to be identity. Well, let's just multiply it with A on the right side again. And then you have A transpose A inverted A transpose A equals identity, the inverse of the other one. And what is important? Well, what is important is essentially that A transpose A, it becomes an invertible matrix. So let's look at this. Is A in this case a matrix which looks like this, or a matrix which looks like this? It has to be a matrix which looks like this. So let's see. This has to be a matrix like this. And I multiplied. Am I doing the right thing? Full stop. It's a matrix which looks like this. That's what I. If this is my matrix, then this is how the transpose looks like. So this is the transpose matrix. Let's call this A transpose. This is A. Now when I multiply A transpose times A, I get a matrix which looks like this. It means a smaller matrix. It's the matrix which has the smallest number of dimensions. If this matrix, that means the number of rows in this case. In this one, I should normally be able to invert. It's not true that it is always true numerically, but normally it should be able to invert. Okay, and then I can write this like this. The same thing happens if we do the right inverse. Now it's just turned around. And I think it comes up next page, hopefully. The right inverse looks like this. So we have A right equals A, make sure I do this right, transpose times A transpose minus 1. Again, you can try this out, multiply A in there. And then you get two terms which should normally cancel, and now A transpose has to be invertible. So now this will work for this matrix. So I have A, this is A, and I'm multiplied with its transpose, which looks like this, and again it gives me the smallest matrix I can get by multiplying the two matrices together, which should normally be invertible. We'll talk about things when things are not invertible. You will see more about that. Okay. Last thing to mention, without going into details, what people like the most is when you want to analyze a matrix, you do what is called a singular value decompositions. And I'm not going to go into this in detail. Also, the book, I think, doesn't go into detail. It's essentially a decomposition of a matrix. All of this here. So a matrix A is decomposed into a matrix U, some special matrix sigma, and V transpose. And what this means, actually, this here is going to be a diagonal matrix. And what it has on the diagonal is the singular values which are directly related to the eigenvalues of a matrix. So this basically matrix will tell you all the eigenvalues, usually in decreasing size. And some of them are 0, something goes wrong. V is characterizing the null space of the matrix, and U is characterizing the range space of the matrix. So this particular piece of linear algebra allows you to directly decompose a matrix into three most important things we want to know about: null space, range space, and singular values or eigenvalues in the end.
And you can get this in MATLAB or any different programming languages, and this helps you to analyze what's going on. It's a medium expensive operator, but it's very useful, just to know about. Good. And we are all done for today. So read this chapter. It's really, I know it's dull, but it's useful to read. I try to give you a little bit of intuitions why it's important, and you will see throughout the course why it matters. All right, see you next week.